Okay, good afternoon, everyone. And now we turn this my name is Alessandro. We turn this last session of talks today on measurement-induced phase transition. And we will start with Alessandro Romito from Manchester University, who will be unraveling measurement-induced phase transitions projected by projective plots.
Thank you for the introduction, and once again, thank you to all the organizers for this beautiful workshop they managed to put together. My talk is on measurement-induced phase transition. Before okay, go like that. So before I start, let me thank all my collaborators on the results I'm going to present, and I would like to spend a few words to say most of the credit is for my PhD student, Chun Leung, whom most of the credit should go, especially for the results on the partial post-selection part, which I present at the end of the talk. And I also have to thank the organizer for at least one of the organizers, for letting me borrow this figure that was used in the introductory talk to just set the field of this workshop. And as you see, there are many ingredients coming together in this workshop, and my talk will sit in this picture. But the fact that interaction with the external path is due to be by quantum detections. So the path will consist of quantum detectors, and the aspects we mostly look at from the system, if we take just the isolated many-body system, will be its information scrambling aspects. So there's pretty universal aspects of many-body interacting systems, and what we are talking about is the fact that we take a system with some isolated initial state where information is inputted in a spatially fixed point, and we let the system evolve. Information will scramble, and the way we quantify that is by looking at a portion of the system and look at the entanglement entropy of this subsystem. And this will evolve in time, as you can see. Can you see my... Is this supposed to work as a pointer, or... And there's none, or... Okay, well, we'll leave with that. So if you look at the plot there, you'll see the way we quantify that is by looking at the entanglement entropy of this subsystem. It will evolve in time until we reach a steady state. And this steady state entanglement entropy will be size dependent. So the larger system size, the larger the entanglement entropy, and this will scale with the system size in what we call a volume order. I would appreciate that. Okay. Thanks a lot. Can you see? Oh. Well, we can live with that. At least I can move the slides. Okay, so we are looking at the entanglement entropy of the subsystem, which, as a rather general rule, will scale with the system size in steady state, and that's what we call volume law. And that it means the system typically thermalized. So that's a behavior we are looking at. And the question is, what does measurement do to that, and why we're interested in looking at an external environment which consists of quantum detectors? So very briefly, when we talk about measurement, what we're talking is simplest example, which is just a century-old Stenger type of measurement. So we're looking at projective measurements, which schematically is represented by the fact that the state size is generally stochastically, so with some probability projected in one of the two eigenstates of the observer we are measuring at. So we can think of the simplest case, if we're measuring the spin, sigma z component, and the system will end up either spin up or spin down. The important aspect is that this will happen depending on the state of the system. And you can also think of that as on a block sphere, if you prefer that representation, in which the system is kicked to the north or south pole. So why measurements? Because measurement compete generically with the unitary evolution of the system. And the simplest case where you see that is the quantum zero effect. So as simple as can be, no many body yet, just a single qubit. And what you see on the right is just the time evolution of a system represented in terms of quantum gates, which are the gray part of the unitary one, and those sorts of diodes represent measurement. So if you have an intercalation of measurement and unitary evolution, what will happen is that the system will evolve as depicted on the block sphere. We will have some unitary part, and then the system will evolve according to different trajectories, which kick the system to the north or south pole. And then again, there will be some unitary rotation and different kicks with different probability depending on the position of the sphere. So generically, you expect a bunch of all those lines evolving along the block sphere, which are quantum trajectories. So why this is interesting, what you see below is that the evolution of a system which is prepared in the North Pole evolves according to an Hamiltonian that should provide quantum coherent oscillation that you look at the probability of being at the North Pole as a function of time. If you perform a measurement, you should see some coherent oscillation, the first part of which is that thick black curve there. So this will change coherently like a cos function. Now, if you start performing measurements at an interval delta t, what happens is that after a while, the system will be projected either to the north or the south pole. And if you perform the measurement frequently enough, the probability of being kicked back to the north pole is increasingly higher. So as a result, for frequently enough measurement, you will get stuck at the north pole. So measurement will block this Fourier evolution state and will localize you to the north pole. What happens in reality is that the system will be stuck around the North Pole for a while, and then there will be some rare events which correspond to jumps in which the system will jump due to the measurement and be projected to the South Pole, and then it gets stuck there, and then again it can be projected back to North Pole. So we will have a system which is stuck either to the North or South Pole, and will jump randomly between these two states. Okay. As a result of that, though, the system will not develop coherence if you think of a single qubit. And what became interesting in the recent, say, 5 years is what is the many-body results of that. And as you can imagine, as for a single qubit, you're blocking a coherent dynamics. For a many-body system, measurement will block the information scrambling of the system, which is due to the unitary evolution. So to be specific, and this is the first system that was started in this context, I just take the simplest many-body system you can think of, which is just one-dimensional spin chain with nearest neighbor interactions. And the way this system has been studied in terms of quantum circuits, so the nearest neighbor interaction is general, indeed, it's just the two qubit unitary gates, which is completely random and flat. So they are measured on the unitary matrices of qubits. And then you perform at random some measurements. The measurement, projected measurement, measures projected system either spin up or spin down, and this happens randomly. So at each side, with your coin, the coin is will give you probability whether you should perform the measurement. So if you don't perform the measurement with probability is 0, you get what you expect. The system is scrambled information, expect a steady state in which the entanglement of this case is volume law, so perfect optimization. The opposite regime is also very trivial. You measure every side every time, which means that after each layer of measurement, the system will be in a product state of spin up and spin down. It will be randomly up or down, but nonetheless, it will be no entanglement what's better. System. So the system is completely unentangled. What is extremely interesting is that if you look at what happens in between these systems, this is a general phase transition. That's what you see depicted here. So in one regime you have the volume law, in the other regime you have the area law. And if you check how the steady state entanglement of scaling system size, you find two different regimes, either volume law or area law. The volume law will change the law of the scale, but there will be a critical point in which your scaling system size becomes critical, and becomes logarithmic. Okay, so the Zinn effect when you go to many body system gives rise to a phase transition between an area and a volume. And that's how this looks like in the real plot. So you see here is the entanglement entropy as function of time for two different values of probability. The first one, entanglement entropy grows and then stabilizes at a certain value. And if you look at insets, what you see is what is the value of the steady state entanglement entropy as function of system size, which on the left scales like volume law, and on the right is an area law. Now, there are some important aspects to this phase transition that makes it quite different from the usual one. First of all, this is a phase transition of non-equilibrium states, because we are measuring, which is accounting energy to the system, and it's also a phase transition of the stochastic system, which means that if you perform such an experiment once, the system does not reach a steady state, but will continue to fluctuate over time. So what we are talking about is a steady state of a probability distribution of states across many realizations of the experiment. Okay. The other important aspect is that we are looking at phase transition in a quantity which is entanglement entropy, which is non-linear in the system state, by given that it's non-linear in the density matrix of the system, so it depends non-linearly on rho, which is that log you see there. And what you see, because we have a distribution of steady state, we're looking at the average entanglement entropy, and the average is the average of the entanglement entropy, not the average of the state. Okay, I will come back in a couple of slides to that, which is important. Okay, before I move on, we have to say this was the first example that studied before around 2018, 2019. And since then, people have studied this kind of physics in different kind of systems. So changing the kind of unitary, changing also the kind of measurements. And as you will see, the results is pretty general. In sense, the phase transition exists quite generally, even if it might depend on the detail. The kind of transition depends on the details of the model and of the implementation you have. So in particular, we want to generalize this not to projective measurement, but to more general measurements which are generally possible for everybody measured. And quite generally, we don't have projections, but the way we describe the measurement quite generally is the fact that we have some system, and from the coupling to the detector we obtain a readout, which is just a real number that depends, which is of course correlated with the system. That's what making the measurement means. But what is important about the measurement is that as for a given readout, you have a back action, which is an avoidable system, and this back action depends on the readout. And because the readout depends on system states, you get a back action which is nonlinear in the evolution of the system. As a result of this, you can also perform measurement in So you can take another step. Instead of making a set of measurement, you can make the process continuous, and this will be described by some stochastic Schrödinger equation. And here you have an example of them, which is the first quantum jumps. So this is the differential increment state, and this depends on the readout R, which you see here. And this readout has stochastic nature, which in this specific case is a constant process. The other important aspect is to look at the coefficient in terms of Ri. This depends non-linearly on O because there are expectation values. In this case, the measurement process is controlled by one parameter, which I'm referring to measurement strength, which you can control in many ways, is the rate of the phasing induced by the measurement, or if you want, is also the coupling between your system and the detector. Now, let me go back to the point I wanted to make before about all this. It's absolutely important that you follow all the stochastic processes of the evolution if you want to look at phase transition. What I mean by that, I mean that if you consider the measurement device as an environment, you can think of averaging over a readout, which would correspond to the typical procedure of averaging over a certain environment. If you do that, it's equivalent to averaging all these possible paths in the Hilbert space for quantum trajectories, and the result would be generally a Hilbert equation. As we know, if we follow this Hilbert equation, what we are looking at is this rho bar, which is the average density matrix. And if we look at that, what we will study will be the second part of this quality yellow box. which will be the average state of the system. For most of the system we are looking at, this average state of the system does not display any entanglement-based condition. That's typically the steady state, a trivial state, that comes from competition part of the Newtonian drive system, which is not compatible with measurements. So the only fixed form of that equation is typically trivial identity matrix, regardless of the coupling gamma to the factor, which means there's no transition there. So that's not what you do. You want to follow each and every trajectory. For each trajectory, you want to compute the entanglement entropy and then average the entanglement entropy. So if you do that, you can do it, as I said at the beginning, for many different systems. In particular, for this continuous one, it will also show a transition. And as I mentioned before, and you see in the table up there, if you look at the first line, these are the critical values, which is the critical exponent, the critical point in terms of probability of measurement strength, which are started from merit. And what you see, in particular, if you look at the critical exponent, this is very different in two cases. What does it mean? It means that some universality in this, in the sense that transition exists generically, no matter what kind of measure you do, but specific to the transition, like universality class, or other features, transition depends strongly on what kind of measurement you're implementing or what kind of unitary evolution you implement in the system. And finally, the other aspect which is crucial here, which has to do with three important ingredients here: stochasticity, nonlinearity, and the fact that we are looking at a nonlinear quantity, is how you do this in experiments. So there are some experiments in that, and these experiments are run on quantum architecture as we have it. What we are showing here is the results from experiment on the IBM architecture. And what you see here is the simplest realization dimension. So we have a number of qubits, let them iterate pairwise, and then you measure them at random with some probability. And what you see in this picture is just an analysis, particularly the right one, which is try to collapse all the data from the trajectory to show that they collapse on a certain finite size scale to construct the critical exponent. Now, what you can see here is that the system size is ridiculously small. It's just L equal 8, which for phase transition is a very small system. On the other hand, this run was done on a 127 qubit system. On one hand, the dark number of qubits depends on the fact we have to use a lot of them to perform the measurement and these sort of things. But the major problem for experiments in this context is what we call the postulated problem. And as I said, this has to do with the essence of this phase transition, which is the nonlinearity of the observable we want, and the fact that we're looking at individual trajectories. And this can be explained very simply. So if you want to measure this kind of thing, what you need to do is to take one trajectory, so take your quantum architecture, reverse state, and then evolve a formal measurement for a long time. You look at state length. Now, for that state that you obtain in this one of this experiment, you should be able to measure some quantity related to the entanglement, so something which is nonlinear in code. To do that, you should do, most straightforward thing with the topology of state. You can do things which are more effective at performing, but in any case, with many copies of that state, you can discuss any condition just to the time. So you will be able to produce several copies of that state. The problem is that state has been obtained by a stochastic process, which means the second time you run the experiment, nobody guarantees you will get that state. So you should run the experiment a certain number of times. And the question now comes, how many times will you run the experiment? Since you're measuring each qubit and you're measuring over time steps t, and each one best scenarios can give you two possible outputs, you have 2 to the L times t kind of possible sample of the system. So you run into the bucket with one exponentially large number of experiments, and that's even more good with phase transition. So you need to have a large system size. So this is part of the problem. And that's what becomes interesting, and that's the question I want to address, is how you can, what becomes interesting to understand that this feature of this phase transition really requires study of the entire ensemble of trajectory. Maybe you can take a single one of them, or you can do something easier. So the question I would like to address in the results that I'm going to present is whether you can take a simpler approach and look at specific trajectory, and whether the phase transition features can be or at least to some extent, have some universality, which doesn't require sampling all the trajectories. So the simplest way to do that, that's theory, no experiment, is let's go back to this equation, and you just single out a single trajectory out of all the possible one. And this is one I'm going to call a not-linked trajectory. So this equation describes, as I said, quantum jumps, which means that quantity, delta m, is Gaussian distributed and can be either 0, 1, and you decide arbitrarily to take one experiment in which that quantity is 0. In a typical experiment, it would mean that you just take trajectory which never emit the photon. If you do that, you see that what you're left with is A, deterministic, B, just a non-emission linear Hamiltonian. You can forget about the term with expectation value because that's just an overall normalization. So from the theoretical point of view, that's enormous simplification because you should study an entanglement property of a non-emission Hamiltonian, and we know very well how to do that, at least in many cases. And people have done that. So you take simple system, which is just an easy model in which you measure the local magnetization, and people have compared the results of the full distribution from numerical simulations with the fact that you measure only the non-emission Hamiltonian corresponding to no click, and the results are the one plotted in the plot here. Forget about, I mean, what you measure on the y-axis is just an indicator of the phase transition. When the quantity is 0, it means there's a phase transition. And the two plots, the green one and the blue one, are for the blue one is for the full trajectories, while the green one here is for the non-emission Hamiltonian. And you see at least some features seems to be the same because the system, the phase transition happens exactly the same point. The x-axis is the measurement strength. So both the single trajectory and the ensemble of them gives exactly the same transition point. Would be good if this is the general feature, but I'm afraid it's not. So you can study just a slightly more complicated problem that shows that this is not general case. So this model is slightly more complicated, and this is one for which I'm going to report my results. And this is essentially one of the simplest cases in which we can try to make a theory, which is a Gaussian free fermion, one-dimensional fermion. The only difference here is that they're phrased in terms of Majorana fermions. If you know what it is, good. Otherwise, you can still get the essence of the results. So what you have here is a one-dimensional chain with just normal fermion hopping, and then you perform two kinds of measurements, which is parity of pairs of Majorana, nearby pairs. These are the blue and the red boxes there. And now you have three parameters here that you can tune: is the unitary strength and the strength of these two different measurements, and this is the phase space is reported in this triangular plot. So what you have is the blue one, which are two area low phases. They have different topological order if you want, but that's not important. At the moment, you have two area low phases, and then the red one, which is not a volume low, you cannot get a volume low in this system, but you get an sub-extensive phase, which is logarithmic scaling. Now, you also have a phase transition between where the orange circle is between the area low and the topological one. You have no phase transition on the other side. There's a narrow blue line going to the top. And if you try to make a finite size scaling of the area to area low, you get a strange critical exponent. Now, if you make the same exercise for the post-selected trajectory, which is no click one, you get qualitatively the same region. In this case, the blue and the red are both area low. And in the middle, you get a logarithmic scaling phase. The shape of them is completely different. In particular, you see that the phase transition is on the left corner, the left side of the triangle disappeared. The other feature is that if you look at critical exponent of the bottom line, this is just a trivial easing phase transition, which is very different from the full trajectory one. So what we have been able to do is to develop a bridge between these two kind of phase space, and this bridge should be in constants as far as Google is correct. We try to construct a theory that allows us to go from one to the other so we can understand to what extent the results of the post-selection can be used to inside the trajectory space. And this is made up of two steps. We have 5 minutes. So the first step is to develop a new tool for the measurement part, which we call partial post-selection. To do that, what we have is a microscopic theory of the detector measurement. And the way is simply the original von Neumann model for measurement. You have a Gaussian pointer, and this pointer shifts to the right if spin is up and shift to the left if spin is down. So if you have a generic spin with two different amplitude, state psi with amplitude psi up and amplitude psi down, you get the proposition of two Gaussians, which are the brown one that you see in the picture. The result of the sum of them is a distribution which, in the limit in which the shift is very small, can be approximated by a Gaussian as well. And now comes the idea. Instead of doing a no-click, which would correspond to cherry-picking a single value from this probability distribution, we just take a range of them. So we take this distribution and we cut at a certain point. So we introduce a new parameter, we're calling it RC. And this is a parameter we can freely control in the theory. If we move a lot to the right, we go to post-selection. If we move that red bar to the left completely, we just include all the data and we're back to the normal theory. Now, we can do that in the continuous limit, and what the result is a modified stochastic Schrödinger equation in the presence of this partial post-selection. This is the yellow box. The first two terms, apart from the Hamiltonian, are the standard one. And the new thing that we introduce is the final term, which, as you see, is non-Hermitian contribution to the Hamiltonian. We call this a partial post-selected stochastic Schrödinger equation. And here are the two limits. If psi is equal to 0, you get a post-selected dynamics. So you kill the fluctuations and you're left only with the non-Hermitian Hamiltonian. The opposite limit, if psi equal 1, gives you back a stochastic Schrödinger equation that you know. So now you have one parameter that you can freely tune to make the bridge that I described before. And now we apply this to the model that I described before, which is the only one I know for which we have a reasonable analytical solution. And the way we do is to make a few adjustments, which gives us some sort of stepping stone that let us walk through this path in a way that's solvable. The first one is just we turn the interaction random, and we don't make it just hopping, but we introduce also superconductivity, so it's completely random interaction which pair nearby Majorana. This will not allow us to see part of the phase space, but we definitely will be able to say something about the area-to-area phase transition. And then we do some mathematical trick. The first one is to take the simplest possible quantity, which is nonlinear in the density matrix. And this is what's called the conditional second Rene entropy. So that's essentially the second Rene entropy between subsection A and subsection B of the system, but including also the detectors, not only in the system. And the final step that we do is what is called the replica trick plus a Choi isomorphism. Anyway, at the end of all this, which I'm happy to discuss, whoever is interested, we end up with the fact that the phase transition can be described by deterministic theory. So we got rid of stochasticity, but we gain an interacting Hamiltonian of a larger system. And the larger system is not made out of Majorana now, but full fermion spin. This is, in principle, if you can solve this Hamiltonian and the ground state, we are done. We cannot, so we have to make another step, which is a bosonization, which is valid only in certain regime. And here are my final results. So the results are the following. If you look just at the bottom line of that diagram, in which you have the phase transition between the two area law, what you get is that the phase transition is still there. And for as long as my approximation bosonization holds, the critical property of the phase transition are the same of the post-selected one. And that's confirmed by numerics, which you see in the plot below. So the x-axis is degree of post-selection. Psi star is the value at which bosonization holds. And you see the orange line, the orange part is the part in which a critical exponent, which is plotted, is 1, which is the easy one. That's what my theory predicts. My theory predicts a breakdown like psi star, and indeed the critical exponent breaks down there. What happened after, I cannot predict, but you see numerically that asymptotically you go to the 5/3 coefficient. And finally, that's my final slide. This is the phase space that we obtained from our theory. So what you see is the upper figure is the one that you obtain for full, so the one down here is the one that you obtain in case of the full stochastic dynamics, and the up downward is the phase space that you obtain in case of post-selection. And Xi, which is this out of plane axis, is the one that controls the degree of post selection, which makes the phase space evolve from one to the other. The important point is the presence of this psi star. For value of size smaller than that, you have a yellow phase, which is a logarithmic phase, which doesn't exist in the full system. And you also have that the criticality of the bottom line is the easy one. And with this, I conclude. Thanks. Okay, so the first one is easy. A partial post selection. What I mean is, if you look at this green curve there, that's a probability distribution of the result of the measurement of a single curve. So if you do a post selection, what you will do, you will cherry pick one of them, a single one of it, and then you repeat by always keeping that value. That's what will be a post selected. What I mean by partial post selection is that I still take a bunch of value, but not all of them. So only the shaded part of the distribution. Now, the way I obtain full post selection is the limit in which that red line just goes a lot to the right, and I recover the full stochastic dynamic, but then the red line fully to the left. That's how we get to limits. Of course, the post selected one is only obtained asymptotically, because you can always have a range of values in this procedure, but that becomes arbitrary narrow. The second part, the partial post selection, still gives you stochastic dynamics, which is this one. What gives you deterministic one is not the partial post selection, is the fact that you develop an effective theory for the environment entropy, or in this case for the conditional environment entropy, average. And for that quantity, you can write a deterministic equation because it's an average quantity. The price you have to pay is that you have to go to larger space. It's a relative. You trade off the stochasticity for the deterministic, but the interaction in the larger space.
Thanks. So, now this sort of is helping you with mode selection problem.
I'm not. I don't think it does. What is done? I mean, at least I'm not aware immediately, and that was not the purpose of this work. I think the purpose of the work was to understand how this, whether the feature of this measurement using time transition really depends on the fact that you have an ensemble trajectory, or whether you can kind of forget the fact that you have an ensemble of trajectories, and the result will be roughly the same across the spectrum of trajectories. And the answer is a mixed one. Generically, no, you need to include the entire set of trajectories. But there is some feature like if you look at just a post select, if you look at post selected one, the universality feature, they survive if you include this fraction of trajectories. So there are some features that the feature generally hang the factorial distribution trajectories, but where gives up resulting different distribution.
Okay, so I think for the second time we should move on. So the second speaker again.
You play first. Yeah, there's an after, yeah.
These videos on TikTok, burning the donuts, speaking,